Good afternoon, everyone. It's been a great day. I've had a lot of fun, amazing talks. It's an honor to be here. Thank you, Team Target, for this amazing opportunity. I'm Sarthak from Addverb, and last decade, I've been working on making robots smarter. But here's the thing. Today, I'm going to convince you that biggest challenge in automation is not a smarter robot or building a smarter robot. It's getting hundreds of them work together as an intelligent system, at scale, in real time, and safely. That's orchestration, and that's a challenge. So every product you've recently bought or gotten delivered goes through this product journey, right? It starts as raw material at a shop floor. It'll go through process to process, turn into finished goods. That finished goods will be moved to a warehouse, a regional warehouse. It is stored. Then it can move to a micro-fulfillment center closer to your house. And finally, it reaches your store shelf or are delivered to you. Each of these nodes are highly complex ecosystems. At Addverb, we automate these nodes where thousands of decisions are happening every minute. So we were founded in 2016. We just celebrated our 10-year anniversary. We have 500 automated warehouses and factories around the world. And we have our manufacturing unit in Noida. So that is where we design, develop, and deploy robots from, all under one roof. One benefit of having your own manufacturing unit is you get to design your own robots, right? Right robots for the right problem. So we have a large portfolio of robots. I couldn't put all of them, or it would have become full of photographs. But we have a Dynamo series. These are mini autonomous cars with a lot of sensors, lidars. They can figure out where they are, how to get to point A to point B. Then we have Zippies for faster sortation. They move straight, they move fast, right? We have our shuttles and cranes for deep storage and retrieval. Forklifts for picking up pallet. And we have our picking assist for faster deliveries. And to bring these all robots alive, we have the software. So I have a 2-minute video which will show you how material moves inside a warehouse, right? What happens inside a warehouse? How do all these robots come together and help in that product journey we were talking about?
Concinity captures inbound data, classifies the SKUs as B2B or B2C, intelligently routing based on business requirements. Dynamo intelligently navigates and optimizes its path for quick material movement. It offers increased safety and improved productivity. Multipro for reserve storage, enabling efficient space utilization. Concinity provides advanced sequencing to accommodate changing product priority and varying volume. Computer vision-enabled robotic system to depalletize cartons of different height and orientation. B2C items to be picked are stored in Quadrant system. Quadrant buffers and sequences crates for optimal availability and maximum throughput. Veloce allows highly flexible and scalable returns handling. Boxit for ergonomic and high-speed picking operations of multi-item and single-item orders. Patented quasi-solution for accurate B2C order consolidation. The packed B2C orders are now ready to be dispatched and are sorted by destination route with Zippy 25 robotic sortation system.
So it's beautiful when all these robots come together and start doing the job. To make this all happen, we have our stack, our ecosystem. So our WMS Optimus will take care of orders, inventory. It decides what needs to happen. Right? Consinity, our West system, sequences, prioritizes these events in real time. So it'll answer when and where. FMS, Movec, will decide how these agents will move around the shop floor to make it happen. Right? So they answer how. Prediction and analytics will help all these layers to make smarter decisions. And at the bottom, we have our hardware, right? All our robots. Right? So we'll be focusing on the fleet orchestration part today. Right? So one thing became very clear, right, when we started our autonomous automation journey, that warehouse is not a set of tasks. It's a multi-agent system. And it has to be modeled as one, right? So what do we mean by that? So you need to model all these agents together instead of silos. You start sharing data, sensing states across the fleet. And you optimize for outcomes rather than paths or time. Right? That could mean one of the robot chooses a longer path if it helps the fleet. So it's an AI conference, right? So when I say agents, most of you are thinking about LLMs, using tools, delegating, planning. Our agents do that too. It's just that some of them weigh around 800 kgs and move at 2 meters per second. Same challenges with mass and momentum. So what are these agents we're talking about? So we have our hardware agents, the physical agents, which are our robots, lifts, forklifts. Then we have the software layer, the decision layer, path planners, task dispatchers, inventory managers. And we have humans, right? Commissioning team, supervisor, operators, all the manual overrides, right? An operator can at any time come and cancel a task. So you have to handle that. Great. So we know what our problem statement is and who the players are. So how do you start? You try to simulate everything, right? You figure out what you can simulate, how you can simulate. You start with single robot. You figure out what it does on a bump, what it does around curves. When will the wheels leave traction? What is the maximum speed you can push it to? You put all these agents together. You test your fleet algorithms. You simulate them continuously. And then you finally get them all together in a digital twin. That is the mirror of the live site. So these robots will do thousands of kilometers before they ever go to a live floor. So after that, you will get your robot and you will train you'll get the physical aspects of the robot, you'll feed them back and repeat the exercise till the parameters are met. So great. We simulate everything, we deploy, job done. Not quite yet. Right? There are a few challenges that you need to close before you get there. First is the sheer scale. You're dealing with so many different agents, right? Some of them are fast, some of them can react very quickly, some of them take time to react. So you can't plan for the best of them, you can't plan for the worst, you have to plan for all of them. Second is you're dealing in a dynamic world, everything is changing. So a few years back, we used to take our robots, train them, teach them the map, and commission them. Everything used to move beautifully. Few months later, we got to know that our robots are struggling. So we go and check. The site just moved on, right? New areas constructed, racks had been moved, new production lines, and nobody told these robots. So we go back again, we reteach the map, and a few months later, the same thing again. So we realize the problem is not the algorithms, it's the idea, right? The map on the robot is a snapshot of the area that does not exist anymore. It has changed, it has moved on. So what do? So we realize we need to make our robots behave a bit more like human beings. They need to learn, they need to adapt, they need to evolve with the environment or they struggle. So we update our data structures, ray tracing here and there. And now these robots can use their own confidence on the position and update the maps. So they turn into little servers moving around the area, which we can leverage. Now, third thing is you want to share data, right? Data is power, data is everything. a lot of these robots can produce huge quantities of data. We have multiple cameras, lidars, and whatnot. Right? So the data that was supposed to give you power is now the one which is choking you. Right? So how do we solve this? So we have to solve this one first before we can do anything else. So we, instead of sharing raw data, can we not share events? Right? We find out the right triggers and only share the events rather than just streaming mindlessly. Because you have to store that data at some place, and GBs per second, multiple GBs per second is impossible to take care of. Another thing, obvious idea would be compression. Why not try compression? So we wanted to do compression, but we thought, why not find the right features from this data? And an idea which is a decade old was the best to get started with, right? Autoencoders. Why they are amazing? You don't need label data. Your input and output are the same. So you train your network, you figure out, the network will figure out what are the critical features. And we were able to see compression ratios of 100x, which was amazing. From the lidar data, the networks were able to figure out the walls. It was able to lose out the noise. And that was just the starting. If you know what you're looking for, you can update your loss function and train it for exactly what you want. So that solves our bandwidth problem. We get smart about it, triggers, latents, right? And another advantage is this data is private by compression. No other layer can understand what this data is except for the decoder, right? Which adds value. Great. So Fleet can talk. What do we want to talk about? What are these conversations going to be about? Well, top three I would choose would be maps, routes, and conflicts. So we were talking about the robots we turned into servers, right? They could figure out, update the maps. But what happens if this robot is working in one area of the warehouse for 3 months, 3 weeks, months? It could happen, right? There is a lot of stuff happening at inbound. This robot never gets to go to outbound. So it comes to outbound. It will take some time to figure out what has happened. We don't want it to go and explore and figure out. Okay? So why not have this representation on the cloud or at the server? So we want our robots to send updates. And when multiple robots are sending us updates, we can make smarter decisions there. So now Fleet can start storing this and sending the updates back to the robot. It unlocks another thing now. Fleet has a live map of the area. Every time something changes on the floor, Fleet knows, which is beautiful, right? Second thing is route optimization. If the agents are too smart, they'll figure out how to reach from point A to point B. Do we want that? So everybody will try to figure out the shortest path, and they'll all take the same path, right? They'll start competing with each other. They'll start racing on the shop floor. We don't want that, right? That leads to something you already know about, traffic. On the shop floor, it can be avoided. So why not few of the robots take a longer path, right? We want to spread out these robots. Now, individually, it's not a right decision for the robot. But as a group, they'll help. So any robot stopping, replanning is wasted time. Rather than let it move slowly. Or even better, if there is another path, take another route. Third is negotiation. 2 robots, 1 corridor. Who will yield? I'm thinking the smaller one will, the bigger one can just bully the smaller one. So we don't want that to happen on the shop floor. We want the right decisions to be taken. Same goes for chargers. Too many robots need these chargers. Who will get it? So all these decisions should be based on urgency. You can model this. Also, we want to ensure a deadlock-free resolution. So whatever decision is taken should not lead to a deadlock. We'll always prefer to have avoid a deadlock rather than to solve for it, because solving a deadlock will require the robot to go back. We don't want that to happen. Great. So now, while we were collecting all this data, certain other opportunities came out of it. Now, every time a robot is moving, we are collecting this data, telemetry data, vibration data. What else can we do with it? So before any robot breaks down, it will give you subtle signals. It could be higher current, it could be vibrations. You don't need to understand what these signals are because so many robots are connected to you. You can just see that this reading is falling away from the distribution, right? You don't have to, and a simple outlier rejection itself can trigger a response to some other system which can send an alert to the maintenance team. So you get these alerts way before the robot breaks down. Now, benefit is the robot doesn't break down, right? Robot breaking down in the peak hour is the worst thing that can happen. Imagine it breaks down in the most important corridor. Now, second thing is, if one of the robot can detect a hazard, why can we not inform everyone that there's a hazard here instead of going this route? Take another one. So a few months back, we were commissioning a site with forklifts. And there was a metal expansion joint on the floor. There was no other way about it. We had to cross it. So every time the robot used to go over it, it used to make a loud third sound. It was unpleasant, to say the least. And so what our engineer did, we had these lot of options in the fleet UI. So they created a small slow zone. Now the robots are gracefully stopping and moving ahead, right? It looks beautiful, customer is happy. I was a bit embarrassed, right? We had this data with us. We were taking vibration data from the IMUs. All that was required to just plug it in and get these slow zones appearing themselves. And that's the thing, you need to have these architectures which allow you to capture these human ideas, or else it becomes impossible. It takes weeks and months of effort. We need to have flexible architectures where you can make it happen in a day or two. Now, third case, especially for the Zippies, a lot of these robots are working in a very tight area, right? They have their graphs, their paths, which are optimized in the digital twin, in the simulation we saw. Now, they were optimized for a certain order profile. The customer gave us this order profile. We assumed that to be truth, and we simulated everything. Over months, these order profiles will change, right? And business has to adapt. And so do the robots. Can we not learn these congestions? Because the fleet will compute, will know how much time it takes to complete an order. So every time the robot fails to do that, we can register that event. We can also analyze congestion patterns. So the moment we identify these hotspots, this information can flow back to the simulation. And we can readjust the weights, simulate everything, and if it is giving you a net positive outcome, it can flow back to the fleet. Right? So in runtime, we can learn these changing patterns, test them out in real time, and flow them back to the fleet. Great. So robots, the fleet becomes more aware about its own congestion and tries to adapt. Okay. So if you put it all together, there's your learning flywheel. You have robots that can sense, so capture the right, you'll have your right models to capture, let's say, wires, water on the floor, or vibrations. You compress it, you share latents, you share events, not raw data. Avoid raw data whenever you can. The fleet will aggregate all this information, try to make smart decisions out of it. Right? You try to make some inferences out of this data you've collected and try to deploy it back. You keep doing this over and over, your fleet gets smarter by the day, right? It eventually will learn these patterns. And you can extend this to multiple patterns that you can learn. For example, how's the traffic at this time of the day, and so on. So the point I started with, the challenge isn't building a smarter robot. We can do that. We can make a robot very smart, right? It can figure out, it can avoid any human being, but we don't want that. We want to orchestrate intelligence at scale, in real time, and safely. And why I use the word safely? This is one of our robots. You can see 15 people standing on it. This is Dynamo 2.5 ton. So safety cannot be a second thought. It has to be part of your complete architecture. So retail makes a promise to its customers that your material will reach to you whenever we said it would, right? Everything I explained today will help our customers keep that promise, right? Thank you.